بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على خاتم الأنبياء والمرسلين نبينا محمد وعلى آله وصحبه أجمعين. This is Math 113, final exam term 222. Let us solve the exam together. The first question, we have given the definite integral from 3 to 7. It's equal to -5. From 3 to 4 is equal to 10. And we need to find the integral from 4 to 7 of 3x squared plus f of x. Well, I have three numbers, 3, 4, and 7. So if this is 3, this is 4, this is 7. So I know that integral from 3 to 7 f of x is equal to integral from 3 to 4 f x cos dx plus integral from 4 to 7 and from 3 to 7 is given, so -5 equals, from 3 to 4 is given, so 10 plus, from 4 to 7 I need the integral of 3x squared plus the integral of f of x. So let me call this I, for example. So I would be equal to, if you take 10 to the other side, -5 minus 10, that's -15. So now let me find the integral from 4 to 7 of 3x squared plus f of x dx. I can write it as integral from 4 to 7 of 3x squared plus the integral of from 4 to 7 of f of x dx, which is equal to -15 here. Okay, the integral of 3x squared would be 3 is just a constant, so it's there. And then integral of x squared would be x to the power 3 over 3. So these two, 3 over 3 is 1. From 4 to 7, okay, plus integral from 4 to 7 of f of x is I, which is -50. So I will write it. Now 3 over 3 is 1, so x to the power 3 from 4 to 7 minus 50. So replace x by 7 first, so 7 cubed minus 4 cubed, and then minus 50. If you use the calculator to find the final answer, you will find that the answer is 284. The second question is find the area of the shaded region. To find the area of the shaded region, I can use a vertical rectangle or a horizontal rectangle. If I use a horizontal rectangle, then I have to divide the region into two regions, because here this curve is to the right of this curve, but if you go to this region, the line would be to the right of the parabola. So it's not, it's easier here to use vertical rectangle. When I use a vertical rectangle and move this rectangle all over the region, always the parabola is above the straight line. Now, the formula for the area, it is the integral of, and the area of this rectangle. Just find the area of this rectangle. So what is the area of a rectangle? The width times the height. What is the width? Well, the width of this rectangle is part of x, so we call it dx. Okay, it is delta x, and then when we use the rectangle, we call it dx. And the height of the rectangle, would be, how do you find the height of this rectangle, for example, if this is 4 and this is 2? 4 minus 2 would be the height of the rectangle. So y of the parabola, which is 3x minus x squared, minus y of the curve, which is the line, sorry, which is x. So that's the height of the rectangle, 3x minus x squared minus x. And x runs from where to where? Well, from 0 to here, and here x is 2. So from 0 to 2. So this integral will give you the area. Now I will combine like terms. I have 3x minus x, so that's 2x minus x squared dx. And the integral of 2x, 2 is a constant, integral of x is x squared over 2, we add 1 to the power, minus x squared, integral of x squared, x cubed over 3, you add 1 to the power and you divide by that power from 0 to 2. You can cancel 2 with 2. So now we replace x by 2, 2 to the power 2 is 4, minus 2 to the power 3, that's 8 over 3. And then minus, replace x by 0. When you replace x by 0, you get 0, minus 0 over 3, so that's 0. So the final answer is 4 minus 8 over 3, or just if you use the calculator, it would be 4 over 3. 12 over 3 minus 8 over 3, 4 over 3. Use cylindrical shells to set up, but do not evaluate, an integral for the volume of the solid generated when the shaded region, this region, is revolved about the indicated axis. Well, the indicated axis is the y-axis. Using cylindrical shells, we use a rectangle parallel to the axis of rotation. So I have to use here a vertical rectangle. Now, when this rectangle is rotated about the y-axis, I'll get a cylinder, and that's why the method is called cylindrical shells. Well, the volume is given by the formula. You need to find also the volume of this cylinder. It's enough to find the volume of this cylinder. So the volume of the cylinder, the height of the cylinder times the area of the base, and the base is a circle, but the formula would be given by 2 pi times r, which is the radius. The radius is the distance from here to here. Okay. Of course, we use 2 pi r because that's the circumference of the circle. Okay. This will give you circumference of the circle, will give you the area of this rectangle when you open the cylinder. If you want, you can go back to section in 6.3, which is about the cylindrical shells. So the radius is this distance, and this distance is just on the x-axis, okay? So it's an x value, so 2 pi x. And then times the height of the rectangle. And the height of the rectangle is the y of this curve. From here to here, it is the y of this curve, minus 0 if you like. So it is 2 minus x squared over 4. And the width of the rectangle is dx delta x. And now x runs from 0 to 2. So this integral will give you the volume when this region is rotated about the y-axis. He didn't ask here to evaluate, although the integral is easy, so you can leave it like this. Calculate the sum of this series, whose partial sum is given. You know, we can calculate the sum in 3 cases. If the FSM is given, partial sum, or the nth term of the partial sum, or we have a geometric series, or we have telescoping sum series. So Sn is given. If Sn is given, then the definition says that the sum, this sum, is equal to limit of Sn when n goes to infinity. That's the definition of the sum of the series. So its limit Sn is given 2n squared plus 3 over n squared plus 1. How do we find the limit if we have polynomial over polynomial? We take the highest power up and the highest power down. And then we cancel n squared with n squared. We have limit 2 when n goes to infinity, and that's 2. So the sum of the series is 2, and that's the answer of the question. Evaluate each of the following integrals. Well, I have sine cube over cosine x. Sine and cosine together, okay, this is trigonometric integrals. So we have, the method says that if you have sine times cosine, sine to the power m times cosine to the power n. So we search for an odd power. If the power of sine is odd, then you take u equals to cosine x. Well, the power of cosine here is odd, but you cannot take u equals to sine x, because if you take u equals to sine x, then you need du, the derivative of u would be cosine x dx, and I don't have cosine x dx. I have dx over cosine x. I have 1 over cosine x times dx. I do not have cosine x times dx. So taking u equals sine here is not correct, will not help you to solve the problem. But the power of sine is also odd. So I can take u equal to cosine x. Then du, the derivative of cosine, is negative sine x dx. Now let us rearrange this integral, but let me also change the x values to u values. X is 0. If x is 0, then u would be cosine 0, which is 1. And if x is pi over 4, then u would be cosine pi over 4, which is 1 over square root of 2. So I have integral from 0 to pi over 4. Sine cube, I need sine x dx, okay, to be du. So I will write it sine square x times negative sine x dx over cosine x. And since I multiplied by negative here, I will multiply by negative outside. So I will have negative integral from 0 to pi over 4. Now negative sine x dx would be du, but u would be cosine. I do not need sine square. So sine square, I have to write it 1 minus cosine square x. course, we know that sine square x plus cosine square x is 1. So I can replace cosine square by 1 minus sine square. Well, now I can change the integral from x to u. So I will change the limits of the integral there. So from 1 to 1 over square root over 2 instead of from 0 to pi over 4. And 1 minus cosine square would be 1 minus u square. And over cosine, that's over u. Negative sine x times dx would be du. And now to evaluate the new integral, I have 1 minus u square over u. I can distribute the numerator over the denominator. I can write it 1 over u minus u square over u, and that's u. U square over u is just u. And now this is easy to evaluate. The integral of 1 over u is just the absolute value of u, and the integral of u is you add 1 to the power u square over 2 from 1 to 1 over square root of 2. You replace u by 1 over square root of 2, so I will have ln 1 over square root of 2. This is positive, so no need for the absolute value, minus 1 over square root of 2 squared, and that's 1 over 2 over 2, and then minus ln 1, that's 0, 1 square over 2, that's 1 over 2. I can write this one as ln 1 minus ln square root of 2, okay, just for simplifying. This is a property of ln. Ln A over B is ln A minus ln B, okay. And 1 over 2 is 1 over 4, and then minus times minus plus half. Ln 1 is 0, so I will have the final answer. Negative 1 over 4 plus half, that's 1 over 4, and then I will write minus ln square root of 2, or even you can write it half ln 2, both are correct. What about this integral? I have square root of 16 plus x squared, so I use trigonometric substitution. That's section 7.3. If you have a square root of a square plus x squared, then the substitution would be x equals a tan theta. This is what we have in section 7.3. So here I will let x equals a squared is 16, so x would be 4 tan theta. And then I need to find dx because I need to change everything from x to theta. 4 is a constant. The derivative of tan theta is secant square theta d theta. So now let me change the integral, but I need to find out this square root would be equal to what. So x is 4 tan theta, x squared would be 4 squared, which is 16, tan squared, which is tan squared theta. I have 16 plus 16 tan squared theta, so I can take 16 as a common factor, and I'll have 1 plus tan squared theta. And 1 plus tan squared theta is secant squared theta. Okay, sine squared plus cosine squared is 1. And when you divide by cosine squared, sine squared over cosine squared is tan squared, and cosine squared over cosine squared is just 1, and 1 over cosine squared is secant squared. So that's an important identity. Tan squared plus 1 is secant squared, so I'll have 16 secant square theta, and then the square root would be 4 secant theta. It could be positive or negative, but we choose a domain in which it's positive. So now I can write the integral as integral. What is x cubed? Well, x is 4 tan theta, so x cubed would be 4 to the power 3. That's 64 times tan cubed theta. And the square root of 16 plus x squared is just 4 secant theta. And dx is 4 secant square theta d theta. So I can cancel 4 with 4 and secant with one of these secants. And I can take 64 outside of the integral. I'll have tan cube theta times secant theta d theta. And now this is an integral of section 7.2. I have tan secant, tan to the power m, secant to the power n. And for the rules or the method says, if the power of tan is odd, then I take u to be secant theta. Okay, please, if you like, check section 7.3 rules again. The derivative du would be, derivative of secant is secant tan d theta. So this would be this will enable me to change from secant to u. So I will have 64 integral. What? I need secant times tan beside d theta. So tan cube, I can write it tan square theta times secant theta times tan theta d theta. All of this would be du. I need secant theta to call it u. I do not need tan square. So I will write tan square as, we said that tan square plus 1 is secant square. So I can write tan square as secant square minus 1. So I can write tan square as secant square theta minus 1 times secant theta tan theta d theta. Now this integral would be, change it to u easily, u square minus 1 times c, all of this is du. And that's it. You can find now the integral of u square, it's keep 64 outside, u cube over 3 minus integral of 1 is u plus c. Okay, let me change back or go back to theta. So the integral, the answer would be u, I replace u by secant theta. So I'll have secant cube theta over 3 minus u, which is secant theta plus c. And now I need to go back to x. Well, what is the relation between x and theta? X equals 4 tan theta. So what would be tan theta? Tan theta would be x over 4. And I know that tan theta is the opposite over the adjacent. If you remember, so TOA. Tangent is opposite over adjacent. So if this is the angle theta, the opposite is x, the adjacent is 4, and I can find the hypotenuse using the Pythagorean theorem. It's the square root of x squared plus 4 squared, which is 16. And this root should be in the question. It is the same root in the question. So the final answer would be 64 times. Now secant, I need secant theta. Well, secant is the opposite of cosine. Cosine is the adjacent over the hypotenuse. So 4 over square root of x squared plus 16. So secant would be square root of x squared plus 16 over 4, and this is secant, so I need it cubed, secant cube over 3, so I will write here 1 over 3 minus secant, which is square root of x squared plus 16 over 4 plus c. If you want to keep the integral like this, it's fine, it would be, it's correct, it's accepted. Here I have polynomial over polynomial, and the degree of the numerator, the polynomial in the numerator is 1 and below is 1, so I have the same degree. So this is section 7.4, and it says if you have equal degree polynomials, or if the degree of the numerator is higher, you need to use long division. We divide 6x by 2x, x cancels with x, and 6 over 2 is 3. And then we multiply 3 times 2x plus 3. 3 times 2x, that's 6x. 3 times 3 is 9. And now I change the signs and I add. When I add, 6x minus 6x is 0, and negative 5 minus 9 is negative 14. So I can write this integral as 3, that's the quotient, the answer, okay, quotient, minus, or the remainder, it should be plus the remainder, but the remainder is negative 14, over the divisor, which is 2x plus 3. All of this with respect to x. The integral of 3 is 3x, and minus 14 is just a constant, and the integral of 1 over 2x plus 3 is ln 2x plus 3 divided by the derivative of 2x plus 3, which is 2. So I should divide by 2. So the final answer would be 3x minus 7, then absolute value of 2x plus 3, of course, plus c. Find the exact length of this curve. Okay, exact length, we call it L, that's the arc length. And it is, since x is given, x from 0 to pi over 4. So I will use dx here. You can find the arc length dx, or using dx or dy. If x is given, I will use dx. So I can write here from 0 to pi over 4. That's x changes from 0 to pi over 4. The formula would be 1 plus y prime square. That's the formula of the arc length. It is in section 8.1. Please, if you want to have more examples about arc length. So from 0 to pi over 4, square root of 1 plus. Now let me find here the derivative. What is y squared? Sorry, what's y prime? What is the derivative of ln? 1 over. Then, using the chain rule, derivative of ln x is 1 over x, but ln u, 1 over u times u prime. So what is the derivative of cosine x? I will write it here. Negative sine x. Well, sine over cosine, I can just write it negative tan x. And then y prime square would be 1 plus, sorry, derivative, y prime square is negative tan x all square. So that the negative will disappear, and I will have tan square x. And then 1 plus y prime square, which is here, would be 1 plus tan square. And 1 plus tan square, we have just seen that it is secant square. And square root of 1 plus y prime square would be square root of secant square. And square root of secant square in this domain from 0 to pi over 4 is equal to secant x. And we have a formula for integral of secant x. It is len secant x plus tan x from 0 to pi over 4. So let me replace x by pi over 4. The answer would be len secant pi over 4 is square root of 2. Tan pi over 4 is 1. Okay. Minus secant 0 is 1. It's 1 over cosine 0. Cosine 0 is 1, so it's 1. Tan 0 is 0. Len 1 is 0. So the final answer is len square root of 2 plus 1. That's the exact answer. Determine whether this sequence converges or diverges. We determine whether the sequence is converges or diverges by finding the limit. So the limit of an, the limit of tan inverse n when n goes to infinity. Tan inverse n is above the function tan inverse x, and the limit of tan inverse x when x goes to infinity is pi over 2. Okay, you know that from the graph of tan inverse. This is the graph of tan inverse. It has two asymptotes, pi over 2 and negative pi over 2. So when n goes to infinity or x goes to infinity, the graph goes to pi over 2. Well, if there is a limit, if there is an answer pi over 2, then the sequence converges. So sequence converges to pi over 2. That's the limit. Determine whether the geometric series is convergent or divergent. If it is convergent, find its sum. You can solve this exam or this question by two methods. I will solve it by two methods. So let me solve it first. He says geometric series. So let me find the first term of this series. I find the first term of the sequence, okay, by replacing n by 1. So 3 to the power 2 times 4 to the power negative 1. And that's 9 over 4. Second term, 3 to the power, I replace n by 2. 3 to the power 3 times 4 to the power negative 2. And that's 27 over 60. Now R would be the common ratio A2 over A1. So 27 over 16 divided by 9 over 4 or multiplied by 4 over 9. So 27 over 9 is 3 and 4 over 16 is 4. So R is 3 over 4. R is 3 over 4. So I have I have the first term and the common ratio, so I can find the sum. The sum of the geometric series is A over 1 minus R. It's given by this formula. A is A1, which is 9 over 4 over 1 minus 3 over 4, and that's actually 1 over 4. 9 over 4 over 1 over 4. 4 cancels with 4, and I get 9. So the sum of the sequence of this series is 9. Now the other method, this is one method, okay? So or this is summation from 1 to infinity. So I have to compare the summation with the definition of geometric series, okay, which is summation from 1 to infinity of A times R to the power n minus 1. So I need to write the sequence or the series into this formula. I have 3 to the power n plus 1, so I need 3 to the power n minus 1. So I can take 3 squared, multiply by 3 to the power n minus 1. This will give you 3 to the power n plus 1 if you add n minus 1 plus 2. And I have 4 negative n, I will take it down. It's 4 to the power n. I write 4 times 4 to the power n minus 1. So I have now, I can write it. I have 3 to the power n minus 1, and I have also 4 to the power n minus 1. So I can write it. This would be equal to okay, 3 squared over 4, that's 9 over 4. And I can write this as 3 over 4 to the power n minus 1. So this would be the series written in this form. So I can determine A by comparison. A would be 9 over 4, and R would be 3 over 4. And that's what we got here in the other method. Okay. And then you continue and find S similarly. S is 9. Then S is A over 1 minus R, and that's 9. Determine whether the series converges or diverges. Okay, I have 3 to the power n over 4 to the power n. And I have n. 3 to the power n, 4 over to the power n, that's a geometric series. But n, 1 over n, that's p series. So this is a combination. So, well, if I call this summation an, and if I take bn as 3 to the power n over 4 to the power n, which I can write as 3 over 4 to the power n, then we know that summation bn, which is 3 over 4 to the power n, is a geometric series with r equals 3 over 4, because you can write this 3 over 4 times 3 over 4 to the power n minus 1. So r, in fact, is 3 over 4, or you can take the first term, the second term, and divide. So less than 1, so it's convergent. And now I can find the limit comparison test. I can find the limit of an over bn when n approaches infinity. Well, an is 3 to the power n over n plus 4n, 4 to the power n, divided by 3 to the power n over 4 to the power n, or multiplied by 4 to the power n over 3 to the power n. So I can cancel 3 to the power n with 3 to the power n, and I will have 4 to the power n over n plus 4 to the power n when n goes to infinity. Now, when n goes to infinity, this is not polynomial over polynomial, but you can see that here I have 4 to the power n only. But between these two terms, the term will be considered when n goes to infinity is 4 to the power n, because at infinity it goes to infinity much faster than n. For example, if n is 1,000, n would be 1,000, but this term would be 4 to the power 1,000. 4 over n, you can cancel 4 to the power n with 4 to the power n, and you have 1. The limit would be 1, and 1 is greater than 0. So you can say by limit comparison test series converges, because summation Bn converges. Can we use the direct comparison test here? We will be able to use the direct comparison test if we can prove that An is less than Bn, because we found that Bn is convergent. Well, n plus 4 to the power n is greater than 4 to the power n, of course. So 1 over n plus 4 to the power n is less than 1 over 4 to the power n. And then if you multiply by 3 to the power n, you get 3 to the power n, okay? So in fact, I can use direct comparison test here. So I can say that 3, this one, I can write this one, okay? I can say that n plus 4 to the power n is greater than 4 to the power n. Then 1 over n plus 4 to the power n is less than. And then, so this question can be solved using both direct and limits. Multiplying by 3 to the power n. And then I have An less than Bn. So by direct comparison test series converges, okay? Because less than convergent is convergent. That's what the direct comparison test says. What about this series? Determine whether the series converges or diverges. Well, I have alternating series. So I'll use the alternating series test, and this would be Bn. The test says find the limit of Bn first when n goes to infinity. N minus 5 over 1 plus 2n. I take the highest power over the highest power. This is polynomial over polynomial. N cancels with n, and the limit would be half. Well, half is not equal to 0. So if you use the alternating series test and you find that the limit of Bn is not 0, then immediately you can say that the limit of -1 to the power n times Bn when n goes to infinity will be plus or minus this number, plus or minus half. So in fact, the limit does not exist. And if the limit of An does not exist, then the series diverges or is divergent by test for divergence. So that's the answer. Another series, well, I can see that I have n, the highest power is n, and the highest power is n cubed. So I can take Bn as n over n cubed, or 1 over n squared. And we know that summation 1 over n squared is convergent because it's a P series with P equals to 2 greater than 1. So I use comparison test here because this is similar to a P series. But I have plus up and plus down, so I need to prove that An is less than Bn if I want to use the direct comparison test. But this is not possible because I have plus up and plus down. So I'll use the limit comparison test. So I'll find limit An over Bn when n goes to infinity. if you want, you can check section 11.4, okay, to get more questions or examples about direct comparison test and limit comparison test. N plus 1 over n cube plus 2n plus 1, that's an, divided by bn or multiplied by the reciprocal of bn. So I'll have n squared here over 1. This is a polynomial over polynomial. Notice that this is n squared times n plus 1. So the highest term in the numerator will be n cube, and in the denominator will be also n cube. N cube over n cube is 1. The limit would be 1 greater than 0. So by limit comparison test, series converges because 1 over n squared is convergent. This one was, yeah, also convergent. Okay. Determine whether this series is absolutely convergent or conditionally convergent or divergent. Well, to check whether the series is absolutely convergent, I consider the absolute value of an. Okay. Now, if I find that this series converges, then the original series would be absolutely convergent. Of course, absolute value of negative 1 to the power n will make it 1. So I have 1 over cube root of n plus 1. Well, this is similar to 1 over cube root of n. But that's a p series with power 1 over 3 less than 1, so it's divergent. So I'll take bn here equals 1 over cube root of n, and summation 1 over cube root of n is divergent because it's a p series with p equals 1 over 3 less than 1. So can I prove, now this is divergent. To use the direct comparison test, I need to prove that an is greater than bn. I can't because the denominator here is greater than this denominator. So actually an is less than bn here. So I'll use the limit comparison test. I find the limit of an over bn. So limit of 1 over cube root of n plus 1 divided by bn or multiplied by the reciprocal of bn. Now taking the highest power up, you can say the term here, cube root of n will be, of course, 1 will not do anything at infinity. Cube root of n will go to infinity. Canceling this one with this one, I get 1. Again, the limit is 1, which is greater than 0. So by limit comparison test, series diverges. Why diverges? Because summation bn diverges. Okay, so the original series, okay, let me call it an, let me call this an. So summation an is not absolutely convergent because I found that this series is divergent. So it could be conditionally convergent. How to find out? I have now to consider the series summation an and test this series for convergence or divergence. Well, it's an alternating series, so I'll use the alternating series test. So bn in the alternating series test would be equal to 1 over cube root of n plus 1. And the limit of 1 over cube root of n plus 1 when n goes to infinity is 1 over infinity, which is 0. And now I need to prove the second condition, bn plus 1 is less than bn. And this is in fact correct because 1 over cube root of n plus 1, which is n plus 2, is less than 1 over cube root of n plus 1, because cube root of n plus 2 is greater than cube root of n plus 1. So this is correct. So by alternating series test, summation AN is convergent or converges. So summation AN is conditionally convergent because it is convergent, but the absolute value is not convergent. So it is conditionally convergent. That's the definition of conditionally convergent. You can find more questions about it in section 11.5. Use the root test to determine whether this series is convergent or divergent. The root test is in section 11.6. You can see more questions about it there. The root test says I have to find the nth root of absolute value of AN. Okay. So this is AN. This is AN. If you, this would be the nth root of absolute value of -2 over n, all to the power n, if you like, because you can take power n, I can write it -2 over n, all to the power n. Then n cancels with n, and I'll have absolute value of -2 over n, and that's 2 over n. After you find this root, you find the limits. And the limit is 2 over infinity, that's 0. Well, the root test says, if this limit is less than 1, then the series is absolutely convergent. He says convergent or divergent. If it is absolutely convergent, then it is convergent, and that's the answer. Find the radius and interval of convergence of the following series. Well, we use the ratio test. So this is a power series. How to find AN plus 1? Well, this is AN, of course. This is AN. Okay, what is inside the series is AN. So AN plus 1, I replace each n by n plus 1. So I have n plus 1 factorial times 2x plus 1 to the power n plus 1 over AN, which is n factorial 2x plus 1 to the power n. N plus 1 factorial is equal to n plus 1 times n minus 1 times n minus 2 until you reach 1, 3 to 1. So I can stop here and write it n factorial. So I can cancel n factorial with n factorial, and I'll have n plus 1 only in the numerator. And I can cancel these two together, and I'll still have 2x plus 1 up, okay? Because I have n plus 1 here, and here n. So inside the absolute value, I write it 2x plus 1. Because x could be any real number, so I need to keep the absolute value. X could be negative, for example. Okay, now I find the limits. The limit of n plus 1 times absolute value of 2x plus 1 when n goes to infinity. If you replace n by infinity, infinity plus 1 is infinity times any number. That would be infinity. So the answer is infinity. The ratio test says if the limit is infinity, then series diverges. So the series diverges for all values of x, except the center, because there is a theorem says that the series, any series, is always convergent at the center. Well, how do you find the center of the series? You have 2x plus 1 to the power n. So you take 2x plus 1 and you put it equal to 0. And you solve this equation. 2x would be equal to -1, x would be equal to -1/2. So this series is convergent only at -1/2. So I can say that the interval of convergence contains only this number. And if the convergence contains only one number, then the radius of convergence is 0 because I cannot go anywhere. So the radius of convergence is 0 in this case. Another series, oh, okay, this is the last question. Determine the radius, and so I use the ratio test, an plus 1 over an. X minus 2 to the power n plus 1. I replace each n by n plus 1. I'll have here n plus 1 square plus 1 divided by an or multiplied by the reciprocal of an. So I have n squared plus 1 up, and here x minus 2 to the power n. I have n squared plus 1 over n plus 1 square plus 1. No need for absolute value here. I can cancel x minus 2 with x minus 2, and I'll still have 1x minus 2 up because the power is higher by 1, okay? So I have absolute value of x minus 2, keep the absolute value because x could be negative. Okay, so let us find the limits. Well, the limits of absolute value of an plus 1 over an would be, when n goes to infinity, here the highest power up is n squared, the highest power down is also n squared. N squared over n squared is 1. 1 times absolute value of x minus 2, so the limit would be absolute value of x minus 2. And the ratio test says, by ratio test, series is the power series, okay, the power series is absolutely convergent if absolute value of x minus 2 is less than. And the solution of this absolute value inequality, x minus 2 should be between negative 1 and 1. And by adding 2 to all sides, negative 1 plus 2 is 1, and 1 plus 2 is 3. So the interval is 1 to 3. Now from here, I can find the radius of convergence. What is the center of the series? X minus 2, put it equal to 0, then x is 2, the center is 2. And 2 is in fact between 1 and 3, so I can find out that my answer is correct up to here, the interval is correct, because the distance from 3 to 2 is equal to the distance from 2 to 1 is equal to r. So the radius of convergent here is 3 minus 2 or 2 minus 1, and that's 1. And now if x is 1 or 3, then the limit would be 1. And if the limit is 1, the ratio test fails. The ratio test fails. So I have to consider these two cases, when x is 1 and when x is 3 separately. So if x is 1, I go back to the series and replace x by 1. If I replace x by 1, I'd have 1 minus 2, and that's negative 1 to the power n over n squared plus 1. Okay, so I have this series, and I need to test this series whether it's convergent or divergent. I have an alternating series, and Bn here is 1 over n squared plus 1. The limit of 1 over n squared plus 1 when n goes to infinity is 0. And Bn plus 1, which is 1 over n plus 1 squared plus 1, is less than 1 over n squared plus 1 because the denominator here is greater than the denominator here. So the series converges by alternating series test. When x is 3, I have 3 minus 2, that's 1. 1 to the power n is just 1. So I have this series. And this series is similar to the series 1 over n squared, which is a p series. N squared plus 1 is greater than n squared. So 1 over n squared plus 1 is less than 1 over n squared. So if I take Bn as 1 over n squared, summation 1 over n squared is convergent because it's a P series with P equals to 2 greater than 1. And since 1 over n squared plus 1 is less than 1 over n squared, so by direct comparison test, the original series, which is this one, is also convergent. So at x equals to 1, the series is convergent. At x equals to 3, the series is also convergent. So the interval of convergence would be, interval of convergence was from 1 to 3, but we found that it's also convergent at 1 and convergent at 3. So the interval of convergence would be the closed interval from 1 to 3. I hope that the solution was okay and you enjoyed solving it together. Good luck. Have a nice time.